The last bit of working with forces for this unit is looking at concurrent forces. We need to make sure we know the vocabulary for the terms that we're going to do here. Concurrent is the first word we need to know. The word concurrent means things are happening at the same time. So if I have concurrent forces, they are all acting on an object at the same time. If we look at number 17 on your packet, it says we have 3 concurrent forces applied to an object. The object is going to be at the intersection of the origin of the coordinate axis system here. It says the first one is at 63 degrees at 75 newtons, so that's the green force on our diagram. The second one is 15.5 newtons at 295 degrees. When we're measuring angles on a coordinate axis system, 0 is going to be our horizontal axis on the right-hand side, so there's 0 degrees. If we are measuring 295 degrees, a number of you told me that we measure from 0 counterclockwise until we hit the angle that we want. So there's 295 degrees, but if we look at the diagram, it says 65 degrees. So how did we get 65 degrees when the text tells us it's 295 degrees? Well, again, a couple of you told me that you subtract 295 from 360 degrees, and that will give us our 65-degree angle. We're going to work with angles that are 90 degrees or less because it makes the math a lot easier. Our last force is at 180 degrees, and it's 100 newtons. And the question we're asked is, what are the magnitude and direction of the equilibrant force? Okay, so there's a second term. Before we get to equilibrant force, we need to define something else. So the next term we're going to define is resultant. The resultant force is the net force acting on the object, or the sum of all the original forces, the vector sum. And the resultant force then can be represented by a single force that can be placed in the diagram that will act the same as all of the original forces. This leads us then to the term that was on our question, the equilibrant force. Equilibrant has this root equili, equal, and the equilibrant force is a force that balances the resultant force to maintain motionless status of our object. So it is equal in size and opposite in direction. To our resultant force. So if we find the resultant force, we know the value and we know the angle of the equilibrant force relative to either a vertical or a horizontal axis. How do we go about this? Well, we need to find some components because we only have one force that's horizontal. Our green 75 Newton force and our blue 15.5 Newton force are at angles relative to the horizontal or the vertical, and so those are the ones we need to find components for. So we'll start with horizontal. We're going to take the horizontal component of all of our forces and add them together. So we have 100 newtons. That's our plain old horizontal force. We're going to take the horizontal component of our 75 Newton force. So that's 75 newtons times the cosine of our angle, and it's pointing to the right. We're going to take the horizontal component of our 15.5 Newton force, so it's the cosine of 65 degrees, and that also is pointing to the right. One force to the left, 100 newtons, two forces to the right, and when we add them together, we need to make sure in our math equation that the left and the right are indicated by either pluses or minuses. In this case, we've chosen to make left positive, so we have positive 100, and negative for the other two. And so our horizontal vector sum is 59.4 newtons. It's positive, so that it is going to be pointing to the left. We're going to do the same exact thing, finding vertical components now, and we'll add all of our vertical components together. Our 100 Newton force is purely horizontal, so it has no vertical components. We're just going to deal with our green force and our blue force to find their vertical components. One is pointing up, one is pointing down. So our green force, now we're going to take the sine of 63 degrees because that is the vertical component way to find it. And we're going to take the sine of 65 degrees for the 15.5 Newton force because that's acting down. In this case, we've chosen to make up positive and down negative. So when we find the vertical force, the total, we're going to get 52.78 newtons, and this is up. So our vertical net is up, our horizontal net is to the left. Now we're going to use those and draw a new vector diagram. So here's our 59 Newton force, horizontal sum. Here's our vertical sum of 52.78 newtons. We're going to use those to make two sides of a right triangle, and the diagonal vector, the hypotenuse of our right triangle, is our resultant. Well, how do we do the math? That's where our friend Pythagoras comes in to play. So we're going to use Pythagorean theorem to calculate the hypotenuse of our new right triangle. So with Pythagorean theorem, we find that our resultant is 79.46 newtons, and is pointing up and to the left. So that is our resultant. That's what R stands for. If we want to find the angle, we can either find the angle relative to the vertical or the angle relative to the horizontal. We're going to look at the angle relative to the vertical. Our horizontal component, 59.4, over our vertical component, 52.78 newtons, opposite over adjacent. That's going to be the tangent of our angle. And our angle is 48.4 degrees. To the left of vertical is the direction of our resultant. I said before that our resultant is the net force, and our equilibrant balances the net force. So we need to find the equilibrant. So if this angle here is 48.4 degrees to the left of vertical, then the angle of our equilibrant is down here to the right of vertical in the fourth quadrant. The size of our resultant is the same as the size of our equivalent. We found that was to be 79.46 newtons. So there's the size of our equilibrant, exactly the same size. The angle is the same. It's just in the opposite quadrant. So we have found the value, the magnitude, and the direction of our equilibrant force. And that's how we work with concurrent forces.